introduction.
Good morning, everyone. Our thesis study entitled Development of Supplemental Study Guide for Basic Electronics Laboratory. My topic for today is experiment number 2, which is common emitter amplifier characteristics. The objectives of this experiment are to demonstrate the operation of a common emitter transistor and to observe and measure some of the important electrical characteristics of a common emitter transistor. The common emitter configuration is used more often than the common base and common collector configuration because it provides current, voltage, and power amplification. An understanding of the basic electrical characteristics of a common emitter transistor is therefore very important. In this experiment, we will observe the relationship between a transistor's base current, collector current, and collector to emitter voltage. We will begin by taking the necessary measurements and then we will plot the transistor collector characteristics curve. Then we will use the curves to determine the current gain of the output. Read the entire procedure before performing this experiment. These are the materials that required in this experiment. One of digital multi-tester, one of 1K ohms potentiometer, 100K ohms potentiometer, one of 1K resistor, one of 10K resistor, two transistor which are C1313 and 2N3904. And now, let's proceed the step-by-step procedure of this experiment. First, plug in your power supply, being sure that the unit is turned off. Second, construct the circuit shown in Figure 2-1. Use the wiring diagram shown in Figure 2-2. Turn potentiometer R1 for maximum resistance and set R4 to mid-range. Third, turn the power supply on and adjust the positive voltage control for 15 volts across potentiometer R1 to control the base current of the NPN transistor and potentiometer R4 to control the transistor's collector to emitter voltage. Resistors R2 and R3 are used to limit the current through the transistor to safe values. Fourth, you will now adjust the transistor base current to a value of 10 milliamperes. To do this, we must turn potentiometer R1 slowly until the voltage across R2. Measure this voltage with your digital multi-tester is equal to 0.1 volt. According to Ohm's law, the current through R2 must now equal to 0.1 volts divided by 10 kiloohms or 10 microamperes. Since this current also flows through the transistor's base, must equal to 10 microamperes. At this time, the base current could have been measured with an ammeter, but that would require opening the current path and inserting the ammeter in series with R2 and the transistor base. Remember that anytime we add a resistance in series, the current decreases. Since we only have 10 microamperes of current flowing in the circuit, it is not a good idea to introduce unnecessary loading in the circuit. Fifth, without disturbing the setting of R1, adjust potentiometer R4 until the transistor emitter to collector voltage is equal to 1 volt. Now measure the voltage across R3. Use this time voltage measurement and the resistance of R3 1000 ohms to calculate the current flowing through R3. Since R3 is connected to the transistors collected with, our calculated value of current also represents the collector current flowing through the transistors. We record this value of collector current in milliamperes immediately below the collector emitter voltage value of volt in the table provided in figure 3. Now, complete the table in figure 2-4 by adjusting to the remaining values indicated and recording the corresponding values of collector current. To do this, simply repeat step 5 and 6 for each of the remaining values in the table. When you complete the table in figure 2-4, we have a permanent record of collected current value over a range of collector to emitter voltage values when base current is held constant at 10 microamperes. Pause. In this measurement, the output characteristics of a C1B13 and PN transistor were observed by keeping the base current constant at 10 microampere while increasing the collector emitter voltage from 1 volt to 6 volt. The collector current rises from 3.05 milliampere at 1 volt to 3.55 milliampere at 6 volts. As the previous transistor test, the rise in collector current is very small as compared to the change in collector emitter voltage, indicating thereby that the C1313 transistor is also operating in its active region. Within this active region, collector current is primarily dependent upon the base current and only slightly on collector emitter voltage. The results confirm the expected behavior of a BJT. Once collector emitter voltage is high enough, the transistor stabilizes and the collector current remains almost constant as this collector emitter voltage increases. this test, the C1313 NPN transistor was again measured, this time with the base current increased to 20 microampere and the collector emitter voltage varied from 1 volt to 6 volt. The collector current increased gradually from 6.84 milliampere at 1 volt to 8.06 milliampere at 6 volts. Though collector current increases is small with respect to the voltage increases, suggesting that the transistor is in its active region. In this active region, collector current is determined by the base current and only slightly depends on collector emitter voltage. Because base current is doubled from 10 to 20 microampere, the collector current is similarly approximately doubled, which is expected base current gain for the C1313 transistor. Overall, the data confirms that the transistor behaves predictably within its active region, which with collector current remaining nearly constant for each fixed base current. And now, let's proceed the step-by-step procedure of this experiment. First, plug in your power supply. Be sure that the unit is turned on. Second, construct the circuit shown in figure 3-1. Use the wiring diagram shown in figure 3-2. Turn potentiometer R1 for maximum resistance and set R4 to mid-range. Third, turn the power supply on and adjust the power's positive voltage control for 15 volts across. Potentiometer R1 to control the base current of the NPN transistor and potentiometer R4 to control the transistor's collector emitter voltage. Resistor R2 and R3 are used to limit the current through the transistor to stay flawless. We will now adjust the transistor base current to a value of 10 milliamperes. To do this, we must turn potentiometer slowly until the voltage across R2. Measure this voltage with your multi-tester is equal to 0.1 volt. According to Ohm's law, the current through R2 must now equal to 0.1 volt divided by 10 kilo ohms or 10 microamperes. Since this current also flows through the transistor base, must equal 10 microamperes at this time. The base current could have been measured with an ammeter, but that would require opening the current tap and inserting the ammeter in series with R2 and the transistor base. Remember that anytime we added a resistance in series, the current decreases since we only have 10 milliamperes of current flow in the circuit. It is not a good idea to introduce unnecessary loading in the circuit. Fifth, without disturbing the setting of R1, adjust potentiometer R1, R4 until the transistor emitter to collector voltage is equal to 1 volt. Now measure the voltage across R3. Use this voltage measure and the resistance of R3 1000 ohms to calculate the current flowing through R3. Since R3 is connected to the transistor's collected lead, our calculated value of current also represents the collector current flowing through the transistor. Record this value of collector current in milliamperes immediately below the collector emitter voltage value of volt in the table provided in figure 3-3. Now complete the table in figure 3-4 by adjusting collector emitter voltage to the remaining values indicated and recording the corresponding values of collector current. To do this, simply repeat step 5 and 6 above for each of the remaining values in the table. When you complete the table in figure 3-4, We will have a permanent record of collector current value over a range of collector to emitter voltage values when base current is held constant at 10 microamperes.
This table describes how the collector current of a 2M3904 transistor varies with increased collector emitter voltage with the base current kept constant at 10 microamperes. Collector emitter voltage increased from 1 volt to 6 volt. The collector current rise only slightly from 1.64 microamperes to 1.73 microamperes. Such a small increase means that the transistor is operating in its active region, since within this region remains a constant after collector emitter voltage has increased. In this region, the current gain of the transistor controls the current and collector emitter voltage barely affects it. The data here shows typical behavior of a BJT operating in active mode. Once collector emitter voltage is sufficiently high, collector current become almost stable, reflecting proper transistor operation.
One.
During this part of the experiment, the base current of the 2N3904 transistor was increased to 20 microamperes, while the collector current was measured versus the increase in collector's emitter voltage from 1 volt to 6 volt. Results showed that collector current increased slightly from 3.28 milliampere to 3.48 milliampere. This slight increase points out that the transistor is still operating in its active region collector current.
And now adjust transistor-based current to a volume of 20 microamperes. To do this, simply turn potentiometer R1 slowly clockwise until the voltage across R2. Measure this voltage with your digital multitester is equal to 0.2 volts. This will cause base current to have a volume of 20 microamperes. 9. Without disturbing the setting of R1, adjust potentiometer R4 until the transistor's emitter to collector voltage measured with your digital multitester is equal to 1 volt. Okay. Now use your digital multitester to measure the voltage across R3, then use Ohm's law as we did in step 6. To calculate the current through R3, your calculated current value represents the transistor collector current and should now be recorded in milliamperes immediately below the emitter collector voltage value of 1 volt in the table in figure 3.5. Now, complete the table in figure 3-5 by adjusting collector emitter voltage to the remaining values indicated and recording the corresponding values of collector current. To do this, simply repeat step 9 and 10 for each value of collector to emitter voltage indicated. Your completed table will show how collector current varies over a wide range of collector to emitter voltage values when base current is equal to 20 amperes.
During this part of the experiment, the base current of the 2N3904 transistor was increased to 20 microamperes while the collector current was measured versus the increase in collector emitter voltage from 1 volt to 6 volt. Results show that the collector current increased slightly from 3.28 milliampere to 3.48 milliampere. This slight increase points out that the transistor is still operating its active region, hence collector current is basically controlled by the base current and not by collector emitter voltage. In this test, since base current is greater, the collector current is higher compared to the previous measure at base current is equal to 10 microampere. The data proves that once the transistor enters active region, collector current becomes almost constant, changing only a little even if collector emitter voltage increases.